In this lecture we talk about elements integral over a ring. So we will give three conditions for an element to be integral over a ring, and all three of them are equivalent. So first we start with the theorem and then we will define. So you start with some ring R, A is a subring of R and X is some element of this ring R. Then the following statements are equivalent. So all three statements are definition of this X being integral over this ring A. So the most common one is this. So you have coefficients A0, A1, A2, An minus 1 in ring A such that you have such a monic polynomial equal to 0. So X is again in R. So this means X is root of a monic polynomial with coefficients in A. Just exactly, coefficients are in A. So this is a monic polynomial, means the coefficient here is 1. Everywhere else it may or may not be 1, but this the leading term has coefficient 1. Now we are going to show that A would imply B, where B is the ring AX. This is A module of finite type. Again notice that X lies in a bigger ring R and A is contained within this ring R. So if you have something like this with A module of finite type, again you can say X is integral over A. So all three might be useful at different points. C, again we will show B implies C. So there exists a subring B of R. So there is a subring B of R, and this subring also contains A as well as this special element X in R. So it both contains X and A. So there exists a subring B of R which contains A and X and which is an A module of finite type. Then also X is integral over A. And then we will show C implies A. So B implies C is very easy to see. You just take B as this AX. So then it satisfies everything, and in B we already have A module of finite type, so we don't have to worry about anything. So now we come to the proper definition. So let R be a ring, A a subring of R, an element X of R is called integral over A if it satisfies the three equivalent conditions A, B and C of the theorem here. So in general the definition in most books is just given like this. So R be a ring, A is a subring of R, an element X of R is called integral over A if it is the root of this monic polynomial right here. So that is, it satisfies an equation of this form. So let us give some examples. So you fix square root of 2 in reals. Now this root 2 is integral over integers since it satisfies an equation x square minus 2 equals to 0, and you can see this is monic. Coefficient of the leading term, which is x square, is 1. Now we come to algebraic integers. So a complex number that is integral over integers is called a algebraic integer. So again square root of 2 is an algebraic integer. So it lies in real, so obviously it lies in complex numbers since it satisfies this equation x square minus 2 equals to 0, and this, as you can see, you can also say it lies in zx. Its coefficients anyway lie in integers. So you can say this also, which is exactly this. Then minus 1 plus this complex I square root of 3 divided by 2. This is also an algebraic integer since it satisfies this equation x square plus x plus 1 equals to 0. Again the coefficients are 1, 1, 1, 1 which lie in integers. Or you can use this. You can see this is the everything is in zx. Again this zeta n equals to 1, root of unity. So this is an algebraic integer since it satisfies this equation xn minus 1 equals to 0. Again this is a monic polynomial. Everything, these AIs are in integers. Now we come to algebraic number. So a complex number that is integral over rationals now is called an algebraic number. So 1 over square root of 2 is an algebraic since it satisfies x square minus half equals to 0. So notice that the leading term here is 1 and this belongs to rationals. So now we are going to say A implies B. So say p is some polynomial. It is a monic polynomial such that p of x is 0. We are precisely going to take this monic polynomial. So this is our p of x, which is 0. So the relation p of x equals to 0, this is called an equation of integral dependence of x over a. So let us call M the a submodule of ring R, and it is generated by, say, elements 1, x, all the way to xn minus 1. Now see, by this a, xn lies in M, because you're going to take all these terms and take it to the right hand side. So xn is equal to minus an minus 1, xn minus 1, all the way like this. But all these terms, so 1 will make sure this lies in M, this x makes sure this lies in M, then this lies in M, so therefore xn also lies in M. So now you multiply by some xj to both sides, so xn plus j, you have this multiplication. So again, inductively, now xn lies in M, so now you can put xn plus 1 on this side, and then you will have xn on this side. So you keep doing inductively, you will see all xn plus j lie in M, because we only need till this portion. After that, this equation is helping us. So xn is in M, then therefore xn plus 1 is in M, and so on. So this ax is the a module generated by all xk. So this is just an a module generated by all xk. So this is just a ring of polynomials. So you start with ring a and then just start adding powers of x. We just set ax equals to M, and then you are done, because M contains all the powers. Essentially we just needed these powers, and then the higher powers come on by inductively. So M contains 1, x, so 1 would make sure that everything of a is in there, and ax is just generated by 1, which will generate all the elements of a, then x, x square, xn minus 1. So this is because M is generated by a finite set of elements, and then these higher powers, these are coming inductively from our this monic polynomial right here. So this monic polynomial is giving the powers inductively. Now we said B implies C is clear because we are talking about a subring B of R which contains A and X, and A is a module of finite type. So B already says A is a module of finite type, so we just set B equals to AX and we are done. So most difficult is to show C implies A. So let us now show C implies A. So for C implies A, we start by a finite set of generators, say y1, y2, y3, all the way to yn. So these are finite set of generators for B as a module over A. So that is B, you can say, is of this form. Every element of B, you can write it like this, A y1 all the way to ayn. Now we also said that B is a subring of R, but X is also contained within B. Now B is a subring of R, it follows that X, Y, I is in B, because X is in B, B is generated by these finite set of generators, so X, Y, I is in B for all of these I's. So for all these generators, I equals to 1 to n. So therefore we have this equation of dependency. So this is in B. This is in B. You can write it as of this form. A1 to Y2 and so on for all n. So there are n equations here. So to see it more clearly, we can expand this and we can have this equations of this form right here. So xy1 is in B because we are talking about I1 to n. So this is in B, and then this we are copying here, and we have y1 to yn. So y1 to yn, and these elements are taken from ring A, A11, A12, A13, A1, and they're taken. So we are just copying this relationship down here. So again, we can talk about xy2, which will also give you a linear equation like this. xy3 will give you a linear equation like this. xyn will give you a linear equation like this, which is just copying this equation down right here. Now we are going to take all these elements on the left hand side. Take this to the left hand side, take this to the left hand side. So once we take this, so take everything to left hand side. So all terms are taken to left hand side. Then we can write this in a matrix form like this. So on the right hand side only zeros are remaining, so only zeros on the right hand side, and so you have x minus a11, which will be multiplied by y1, minus a12 y2, minus a13 y3, and so on. So here you have x y2 right here, so you get minus a21 right here, then you have x minus a22 y2, and again same thing. So you can do the same thing here. So now you see on the diagonal is where x is lying. So this we can write in a more fancy format as a bunch of n equations rather than the matrix form. You could write it like these n equations, taking everything to the left hand side. So before putting into the matrix form, we took everything to the left hand side. This equation you can write like this. So these are the y's, aij's, as you can see, and this delta ij is just our Kronecker delta. So delta ii is 1 and delta ij is 0 for I not equals to j. So that just ensures that the x, when you put it in the matrix form, the x is on the diagonals as you see here. Now we want to solve this set of equations, so we will use Cramer's rule to solve it. So again, what if we took everything on this side, this was a system of n homogeneous linear equations in y1 to yn, and you write d for the determinant of this. So the determinant of this entire thing is d. Now recall Cramer's rule. So what we did in Cramer's rule, you had a determinant, you said dy1, and you set it equal to some d1 here. What was this d1? This d1 in Cramer's rule we obtained, you focused on this matrix, this n by n matrix, and you take whatever was here. Here it is 0 0 0, but in Cramer's rule it could be anything here. You take this column and put it right here. So if you put it right here, replace this first column with these zeros, so that gives you d1, and obviously this will be 0 because if you put zeros here, expand by first column, you will just get zeros. But for Cramer's rule you also again do dy2, which you set as d2. For d2 again you focus on this matrix, keep all the columns except column 2. So column 2 you will replace with the column here. Here you have zeros, so you put zeros here. Again you can expand this by column 2, you will get 0, and so on. So the calculation leading to Cramer's rule will show that all of dy are 0 for all I. So this means db is equal to 0 for all b, because every b is written like this. So if you multiply from d here, you have db, so a dy1, a dyn, everything here will become 0. So you are just left with some db here. So all db would be 0, but b is a ring, in particular d of 1 is 0. So only thing it means is that the discriminant or determinant is 0. So determinant is 0. So d, which is a determinant of this matrix, determinant is 0. So what does determinant 0 means? So determinant, when you expand this will become a polynomial, and this polynomial will be a monic polynomial because we are going the highest order term appears in the expansion of the product of the entries on the principal diagonal. So because you can expand it anyway, but we can expand it by first row. If we expand it by first row, you take this and you will multiply with determinant of this. So now here you expand again by first row, so then you will focus on this minor here, then you again expand by first row, then you focus on again the minor here. So essentially when you start expanding from here, all the terms which contain x will be precisely coming from multiplication of the terms along the diagonal. So this multiplication of the terms along the principal diagonal is what will give you the monic polynomial. Obviously you will get a monic polynomial because this will be the highest term. So you have x minus a11, x minus a22, and so on to x minus a n n. This gives you higher term. As you can see, x to the n you will get from here, which is a monic polynomial. Determinant we are setting it equal to 0. So once you expand it, you get a polynomial in x which is monic, and it is set equal to 0. So you get a monic polynomial, and x is satisfying this monic polynomial because x is in the polynomial.